Welcome to the deep dive. Ready to explore something pretty cool? We're going to be diving into AI image generation today, specifically diffusion models.
Yeah, these things are really making waves, They're creating some seriously realistic images.
It's kind of like magic, right? You start with just digital noise, and boom, a photorealistic image appears.
Exactly. But like any good magic trick, there's a clever method behind it. We're going to be looking at a research paper from 2020 to break it all down. It was presented at NeurIPS.
Oh, cool. NeurIPS. That's a huge AI conference, right?
Definitely one of the biggest. The paper is called Denoising Diffusion Probabilistic Models, and it's considered one of the foundational papers in this whole diffusion model field.
So how do these models work? I'm picturing some crazy complex algorithm churning away.
It's surprisingly straightforward at its core. Imagine you have a super clear picture and you start adding static to it.
Like the fuzzy noise on old TVs.
Exactly. You keep adding more and more until the original image is totally gone. It's just noise. That's the first step called forward diffusion.
Okay, so we're basically destroying a good image with static, not seeing the magic yet.
Well, hold on. The magic happens when you reverse it. A diffusion model learns how to undo all that noise. It starts with pure static and slowly removes it, step by step, until the original picture reappears.
Whoa, so it's like rewinding that image degradation.
You got it. It's like taking that fuzzy TV picture and gradually sharpening it until you see every detail. We call that reverse diffusion.
Okay, that's pretty clever. But how does it actually learn to do that, to remove the noise like that?
So during training, the model sees a ton of images and learns to predict what noise was added at each step in that forward diffusion process.
So it's like, guess the noise, but for AI.
Yeah, something like that.
Got it.
And as it gets better at guessing, it gets better at reversing the whole process. Starts with static and ends up with a clean image.
So it's not memorizing images, it's learning the whole pattern of how noise is added and removed.
Exactly. And that's where things get super interesting. This whole removing noise thing is closely related to something called denoising score matching. It's a technique that helps the model understand how to, go from a noisy image to a clean one.
So it's not just removing noise randomly, it's like it's following a map to guide it towards a realistic image.
That's a great way to put it. This whole denoising connection is key because it shows that diffusion models aren't just memorizing stuff, they're actually learning the fundamental structure of what makes a realistic image. They're basically learning the grammar of images.
Okay, that's mind-blowing. So we've got this two-step process, forward diffusion, where we add noise and then reverse, where the model learns to remove it. But where does the actual creating images part come in?
That happens during the reverse diffusion. You feed the trained model pure static, and it transforms that noise little by little into a totally new image.
Hold on, you're telling me we can create images from random noise? That sounds crazy, like some kind of alchemy.
It might sound like alchemy, but it's actually a pretty elegant mathematical process. And you know what's even more fascinating? The way diffusion models make these images is similar to something called progressive decoding.
Progressive decoding. I don't think I'm familiar with that one.
Imagine getting a puzzle but in stages. It starts super blurry, and then you slowly add pieces to get the full picture. That's what these models do when they're generating an image.
Okay, I think I'm starting to see how all these concepts connect. Denoising, score matching, progressive decoding. It's like they're all part of the same puzzle.
Exactly. And this puzzle tells us a lot about how information works, how it's structured and processed. But let's not get ahead of ourselves. We should probably break down this whole progressive decoding thing a bit more.
Yeah, let's do that. I'm curious to see where this goes.
So remember that puzzle analogy. The research paper actually uses this thing called rate distortion to analyze it. It's basically a way to figure out how much info you need at each stage to, rebuild the picture properly.
So it's like finding the most efficient way to send those puzzle pieces. You don't want to overwhelm someone with too much all at once.
Exactly. And the paper shows these diffusion models are pretty good at that. They kind of gradually reveal the image, adding just the right amount of detail at each step.
That makes sense, like building a house brick by brick.
Yeah.
You wouldn't just try to put up all the walls at the same time.
Haha. Good analogy. And this step-by-step thing, it makes these models super adaptable too. They can generate images at different resolutions, different levels of detail. It all depends on how many steps you use in that reverse diffusion process.
So it's like having a volume knob for image quality. You can dial it up or down as needed.
Exactly. Now, you might be wondering how this stacks up against other ways to generate images. like those pixel CNN models we mentioned before. Well, it turns out diffusion models can be seen as a more general version of those, but with a more flexible way of adding info.
Can you remind me how pixel CNNs work again? It's been a while.
Sure thing. They create images pixel by pixel, like a super careful artist, coloring in each little square on a canvas, very step by step.
Right, right. So diffusion models are more like an artist who uses broader strokes, filling in details across the whole canvas gradually.
Precisely. And this might be why they can create such high-quality images. They're not stuck working on one tiny piece at a time.
So these diffusion models are making some serious waves in the AI world. What kind of cool applications are people exploring with them?
Well, one area that's getting a ton of attention is image editing and manipulation. Remember how we talked about them learning the grammar of images? That understanding lets them do some really wild things.
Ooh, like what? Give me some examples.
Okay, so imagine you have two pictures of faces, right?
Mm.
And you want to smoothly transition between them, kind of like a morphing effect. Diffusion models can handle that, no problem.
Yeah.
You can also use them to change specific features, like someone's hairstyle, age, even their expression.
Whoa. That's like AI-powered Photoshop.
Hmm.
Are there any examples in the research paper showing this?
Yeah. Figure 8 shows some pretty impressive results with manipulating faces. You can actually see how they can blend facial features, making realistic transitions between different identities.
That's wild. It's like watching one face slowly morph into another, and it's all done by messing with the noise in that latent space, right?
Yep. It's like having a bunch of sliders controlling different aspects of the image. You tweak the sliders and the model does its thing.
I'm starting to see the creative possibilities here. It's like giving artists a whole new set of tools.
Definitely. And we're just scratching the surface. They can be used for way more than just image manipulation. They could change other fields too.
Okay, I'm hooked. Tell me more about these other applications. What else can they do?
Well, for one, they're amazing at data compression. Remember how we talked about them being efficient with information? That makes them perfect for compressing images and videos, which could totally change how we store and share all that stuff.
Wait, so they could help us create smaller file sizes without sacrificing quality? That would be huge for things like streaming services and online storage.
You got it. And because they can understand the underlying structure of data, they're also great for representation learning, which basically means extracting meaningful features from, complex data.
So they're not just good at making images, they're good at understanding them too.
Exactly. This feature extraction thing makes them useful for stuff like image recognition, object detection, even analyzing medical images.
It's like they're not just artists, they're scientists too.
Haha, love that. Oh, and there's even more. People are looking into using them for creative applications in fields like making music, discovering new drugs, even designing new materials.
Wow, the possibilities are endless. But before we go too far down that rabbit hole, maybe we should also talk about, the potential downsides. Any technology this powerful can be misused, right?
You're absolutely right. We got to be realistic about that.
So what are some of the risks or concerns with diffusion models?
Well, one worry is that people could use them to create super realistic fake images or videos, like those deep fakes. It could make it really hard to tell what's real and what's not, which is bad news for stuff like misinformation and propaganda.
Yeah, that's a scary thought. It's like giving anyone the power to create their own reality.
Exactly. And like any AI, there's also the issue of bias. If it's trained on biased data, the images it makes could reflect that bias, which could reinforce harmful stereotypes or even be used for discrimination.
So we really need to be careful and develop these models responsibly. We have to think about the ethical side of things too.
Absolutely. We can't just ignore the potential downsides while we're busy getting excited about all the cool stuff.
Okay, so we've covered a lot of ground here. We've talked about how diffusion models work, what they're good at, some exciting applications, and even some of the ethical stuff. I feel like I've learned a ton.
It's been a pretty wild ride, haha. Hopefully you've enjoyed diving into these models with us.
I definitely have. It's amazing to see how AI is always changing and pushing the limits.
And we're just getting started. Who knows what amazing creations and discoveries are waiting for us?
Before we get too lost in the future, let's take a second to appreciate the research that got us here.
You're right. These researchers really laid the groundwork for a whole new area of AI.
And they explained it all so well. It's technical, but still easy to understand.
I agree. This paper shows that research can be groundbreaking and beautifully written.
Speaking of the paper, I want to hear more about the specific experiments they did. They didn't just come up with this idea, they actually tested it out, right?
Absolutely. They did a bunch of experiments to see how their diffusion models performed, comparing them to other state-of-the-art methods.
So they had to prove that their approach actually worked. What kind of tests did they run?
Well, they tried their models on several benchmark data sets. One was SciFAR-10, which is a collection of thousands of images across 10 different categories like airplanes, dogs, cats, stuff like that. It's a classic data set for testing image generation models.
So like the AI equivalent of a test track. They can race different models against each other and see which one comes out on top.
Exactly. And on SciFAR-10, their diffusion models did really well, even beating out other popular generative models like GANs.
Wait, they beat GANs? Those adversarial networks that were like the big thing a few years ago? That's huge.
It was a pretty big deal. And they weren't just good on SciFAR-10, they also tested their models on other datasets, including Celeb HQ, which is a dataset of high-resolution celebrity faces.
So they weren't just making blurry blobs, they were generating realistic faces.
Yeah.
That's impressive.
And remember FID score, they used that to measure the quality and variety of the generated images.
Remind me about FID score again. What exactly does it measure?
Basically, it tells you how similar the AI-generated images are to real ones. A lower FID score usually means better quality and more diversity. And their diffusion models got state-of-the-art FID scores on several datasets, so realistic and diverse images.
So they weren't just creating the same image over and over, they were generating a whole bunch of different ones.
You got it. And the paper actually has some really cool visual examples of the images. You can see for yourself how realistic and detailed they are.
I'm definitely going to check those out. But they didn't just stop at testing on standard data sets, right? They probably wanted to understand why their approach worked so well.
You're right. They did something called ablation studies, which are basically controlled experiments. They tweak different parts of the model to see how it affects things.
So it's like taking apart an engine to see what each part does, how it helps the car run.
Perfect analogy. And through these ablation studies, they discovered some really cool things about how these models work.
Okay, spill the beans. What did they learn?
For example, they found that predicting the noise directly worked way better than trying to predict the clean image itself. So it supports the idea that these models are basically becoming expert noise detectors.
Interesting. It's like they're teaching the model to recognize the specific fingerprints of the noise that was added earlier.
And their studies also showed how important their training method was. It focuses on removing the noise at the highest levels first.
Ah, so they're starting with the hardest part of the puzzle and working their way down.
You got it. And that approach gave them much better results. It's like tackling the toughest challenges head-on, which sets you up to handle the easier stuff later.
Okay, so we've talked about how they work, what they're good at, exciting applications, but what about their limitations? Are there things they're not so good at?
That's a great question. And just like any technology, diffusion models have some limitations. One thing is that they can be computationally expensive to train and run.
So you need a lot of computing power to make these things work.
Yeah, especially if you're dealing with high-resolution images or more complex tasks. But hey, researchers are working on making them more efficient.
Good to hear. Are there any other limitations? Any specific types of images or tasks they struggle with?
Well, one interesting thing is they seem to have a harder time with eyewear.
Eyewear. You mean like glasses and sunglasses?
Yep. They can handle most facial features just fine, but eyewear seems to trip them up.
Why do you think that is?
It might be because the model has trouble merging those two very different visual elements, you know? The face and the eyewear, maybe it's trying to blend two things that just don't mix well.
Like trying to mix oil and water.
Haha, exactly. But, you know, this is just one example, and researchers are always working to improve these models.
So this tech is still evolving, and we can expect even cooler results in the future.
Absolutely. The field is moving so fast, and we'll definitely keep seeing breakthroughs in AI-generated imagery.
I'm excited to see what the future holds. But before we wrap up, we should acknowledge the bigger picture. We talked about misuse, but what about the good stuff? How can diffusion models benefit society?
That's an important point. And honestly, the possibilities are really exciting. Imagine using them to improve medical imaging, helping doctors catch diseases earlier and more accurately.
That would be incredible. It
Yeah.
could revolutionize healthcare. What other positive impacts do you see?
They could also be used to create personalized educational content, tailoring it to each student's needs. Or even help us design more sustainable products, minimizing waste and resource use.
It's like using AI to solve some of the world's biggest problems.
Exactly. And this is just the beginning. The potential benefits are huge.
It's inspiring to think about how this tech could make the world a better place.
It reminds us that AI isn't just about making cool images. It's about using technology to solve real challenges and unlock new possibilities.
Well said. But before we get too philosophical, one last thing I'm curious about. We've been talking about images, but could this same approach be used for other types of data too?
You're on the right track. Diffusion models aren't just for images. Researchers are already trying them out with audio, video, even text.
So we could use them to make music, create realistic 3D models, even write stories.
The possibilities are definitely there. Early research shows it might be possible. We're already seeing some cool results with audio generation, and I bet we'll see even more soon.
It's like we're just starting to explore the creative potential of this technology.
Exactly. Who knows, maybe someday you'll be using a diffusion model to compose your own symphony or write a bestseller.
Uh-huh. Now that's a thought. Thinking about these diffusion models, I'm wondering how they fit in with all the other AI image generation stuff out there. Like we talked about GANs and VAEs, but how do diffusion models compare to those?
Yeah, good question. It's always helpful to see how all these different techniques kind of relate to each other.
Totally. Like those GANs, the generative adversarial networks, they were all the rage a while back.
Hmm.
That whole idea of two networks battling it out to create realistic images, that was so cool.
Yeah, that was a pretty revolutionary idea. You have one network, the generator, trying to make images that look real, and the other, the discriminator, trying to spot the fakes. They basically learn from each other in this, like, back and forth process.
It's like an AI art forgery competition.
Yeah.
But as cool as they are, GANs can be a real pain to train. Sometimes they get unstable, and the generator ends up making the same limited output.
True, true. And that's one area where these diffusion models seem to have an edge. They're usually more stable during training and can make a wider variety of outputs.
So diffusion models are more like a patient artist carefully refining their work, while GANs are like a wild, unpredictable painter who might create a masterpiece or, a total mess.
Uh-huh. I like that analogy. Another big difference is how they actually make the images. Jan spit out the whole image at once, in one go. Diffusion models, like we've been talking about, take it step by step, slowly removing the noise.
That gradual approach seems to be key to their success, capturing all those little details and creating images that are both realistic and diverse.
Exactly. And then there are VAEs, the variational autoencoders. They work by learning a compressed representation of the data, like creating a code or a blueprint of the image.
Right, like creating a zip file for an image, you can squeeze all the information in without losing the important stuff.
And then they use this compressed version, this blueprint, to reconstruct the image. VAEs are awesome for understanding the structure of data, but they often struggle to create images as sharp and detailed as GANs or diffusion models.
So it's a trade-off. VAEs are good at understanding data, but maybe not as good at making stunning visuals.
You got it. Each model has its strengths and weaknesses, and they're all constantly evolving as researchers come up with new ways to improve them.
It's really cool to see how these different approaches sort of play off each other and how they're pushing the boundaries of what AI can do. It's like we're watching an AI art movement unfold with new styles and techniques popping up all the time.
And the best part is we're just at the beginning. Who knows what incredible creations and discoveries are waiting for us as these technologies keep getting better.
That's what makes it so exciting. We've come a long way from those early days of blurry, pixelated images. Now we have AI models that can create images almost indistinguishable from real photos.
It really is amazing. And as we've seen with these diffusion models, these advancements aren't just about making pretty pictures. They're about understanding information itself, how it works, and how we can change it.
It's like we're unlocking the secrets of how we see and create. But before we go too deep down that rabbit hole, I want to thank you so much for joining me on this deep dive into diffusion models. It's been an incredible journey.
The pleasure was all mine. I always love talking about these cool AI developments with a curious audience.
And to our listeners, thanks for tuning in. We hope you enjoyed exploring diffusion models with us, and maybe you even learned a thing or two about this game-changing technology.
And if you want to dive even deeper, definitely check out the research paper we've been talking about, Denoising Diffusion Probabilistic Models by Jonathan Ho and his colleagues. It's a super interesting read, even if you're not a deep learning expert.
And remember, the world of AI is constantly changing. So stay curious, keep exploring, and who knows, maybe you'll be the one making the next big breakthrough.
Until next time, keep on diving deep.
See you on our next deep dive adventure.